Hello, you're all very welcome to this video that looks at how linear mathematical models apply in an everyday situation. Seamus Balliu is my name, and this video is for first year science and electronics students at Dundalk Institute of Technology. So we'll make a start. So the idea is, how do mathematical models apply in certain situations? So gravity and the quadratic model is easy to visualize in some of the following situations. So in a football game where somebody kicks the football, the ball kind of rises up in the air and it eventually falls back down into the ground again. A space rocket follows a quadratic path, and there's what we call trajectories, and they follow a quadratic path. But in this video, we're interested in linear models. So if we look at this parabolic path here, or quadratic path, if you take a small section of it, locally that looks like a straight line. So for example, if somebody fired a javelin at great speed, initially it would appear to follow the path of a straight line. So for the purposes of this video, we'll assume that the javelin follows a straight line for the first period of time, and then it eventually starts to fall down. So we've drawn a guy here holding the javelin. So let's just say it's 1 meter above the ground at time 0. And as the time passes along, so we view the axis along there as the time axis. And the question is, how high is the javelin at a particular time? So if we kind of plotted the height of the javelin at different times, and let's say these are the results for a particular situation. At time 0, height of the javelin is 1 meter, which we saw a moment ago. After 1 second, it's gone to 4 meters. After 2 seconds, 7 meters, and so on. So we're interested in establishing a pattern between these figures. So if you look at these figures here just for a moment, can you sort of spot a pattern? So the times are going up in the space of 1 second, and the height, you can look at the gaps. There's a regular gap of 3 seconds. So that might point to the relationship between the time and the height. So the height depends on the time. We call the time the independent variable, whereas the height depends on the time. After a particular time, the height of the javelin has reached a particular figure. So in this case here, it's fairly easy to observe what's happening. The gaps are 3 each time, and the initial height was 1. So effectively, h is equal to 3t plus 1. So it doesn't matter what the time you pick. Let's pick 4 there, for example. The time is 4. 3 4s are 12, plus 1 is 13. Now, the beauty of this linear relation is that if you pick a time between 2 and 3, let's say you went 2.8, so you could now work out what the height is at 2.8 seconds by substituting 2.8 in for t. So that's just what we've done here. If the time is 2.7 seconds, h equals 2.7 times 3 plus 1 equals 9.1 meters. And then we could ask the question, if the height is 52 meters, or when is the height going to be 52 meters? So all we do is we substitute 52 in for the height and work out what the time is. So 52 is equal to 3t plus 1. Take away 1 from both sides, and we get 51 equals 3t, and divide both sides by 3. So t is equal to 17. T is equal to 17 seconds. The height is 52 meters. So here's our first example now that we'll start from scratch. If the time is 0, the height is 3.7, time is 1, the height is 6, and so on. Now this might be slightly a bit more difficult to see because of the decimals. But again, the regular pattern kicks in, so the example will be more or less the same as the previous one. So notice the gaps. The gaps are 2.3. So in the space of every second, the javelin rises by 2.3 meters. Suppose we should have specified, it's kind of assumed, the time, we're taking the time to be in seconds and height to be in meters. The starting height is 3.7 meters. So we've come up with the equation h equals 2.3 t plus 3.7. So at time 0, the javelin has a height of 3.7, and then over the space of the next second it rises by another 2.3, and it keeps rising by 2.3 meters every second. So that's why it's h equals 2.3 times t, multiplication is understood there, plus the initial height. So this 2.3 figure is what we call the slope. So it's the gap in the figures, but geometrically it's what we call the slope or the gradient. And the 3.7 is the initial height, or sometimes we call it the intercept or the y-intercept. So usually, maybe in school, you might have taken the x-axis, so the independent variables will be referred to as x, and then y depends on x. So we'll kind of come back to that. So x is usually used for that first row there, and y, but because we're doing a different application, we go t and h. Now, in school, you might have learned this little formula here, the relationship between x and y. So if that's the x row, and if y is the second one there, y is equal to mx plus c. Now we don't have y. Instead of y, we've got the height, and instead of x, we've got the time. So h is equal to mt plus c. So m is the symbol for the slope. We usually denote the letter m for the slope, and c is for the initial height or the initial value. So in this example, we consider a javelin again. We have different values this time. So if t is 0, h is 4.5, 2.3, the height is 8.41, and likewise for 5.1, the height is 13.17. Now the gaps don't appear to be regular this time, so it might be a wee bit harder for us to figure out the relationship between h and t. So at this juncture, we need to go back now and consider the slope in a little bit more detail. In the previous examples, you could look at the gaps and figure out what the slope was. So we just take a break from that example for the moment and just explore the idea of a slope. So in this situation here, we have a line and it has a certain slope or a certain gradient. And as illustrated, for every 6 units, the line rises by 3 units. So what's the slope on that line? So effectively, all we do is the slope measures the steepness. How steep is that line? But obviously this line here is a little bit less steep than that one over 4 units. That one rises by 6 units. So the slope measures the steepness. The slope is equal to the rise, or the vertical value, the vertical height, divided by the run, or the horizontal width. So in this first example then, the slope is equal to 3 divided by 6. 3 over 6 is equal to a half. And in this one here, the slope is equal to 6 divided by 4. 6 divided by 4, which is 1.5. So what does the slope of 0.5 for this line here mean? What does the slope of 0.5 mean? Slope of 0.5 means for every unit on the horizontal, if you move along 1 meter, you would rise by 0.5 meters. So back to the example that we were looking at. So we'd like to find the slope. The javelin follows the path of a straight line. So what's the slope of the javelin going to be? So if we take 0, at time 0, the height of the javelin is 4.5. And at 2.3 seconds, height of the javelin is 8.41. So again, we can draw a little triangle underneath there. So we get a run and a rise, or a horizontal width and a vertical height. So we know the run, or the horizontal width there, is 2.3, and the corresponding height or rise is 8.41 take away 4.5. So 8.41 take away 4.5 is 3.91. So we know the slope is the rise 3.91 divided by the run 2.3, which is equal to 1.7, or it's the vertical height divided by the corresponding horizontal width, and the slope is 1.7. So for this particular javelin in the question, we now know the slope is 1.7, and we know the initial height is 4.5. So again, using our y equals mx plus c, or h equals mt plus c, m is the value of the slope, m is 1.7, and the c value, the initial height, is 4.5. So h is equal to 1.7t plus 4.5. Now, going back to the set of data that we had for that previous question, rather than draw the diagram and start thinking out how to do the question, there's a nice school formula that most of you would have done in school. So going back to the x and y mode, if they're the x figures and if they're the y figures, so we could call the first point x1. So x1 is 0 and the y1 corresponding y value 4.5, x2 2.3, and y2 was 8.41. And the formula more or less just reproduces what we did before. The vertical height is 8.41, take away 4.5, and that follows this formula here. Y2 minus Y1, 8.41 minus 4.5, over x2 minus x1, which was the horizontal width. And you remember we went from t equals 0 to t equals 2.3, and we called that 2.3 the last time. And again, this little formula gives you the same result. So the slope m equals 1.7, and you can use this school formula here, where you have the first point x1, y1, x2, y2. It's important, if this is x1, then the corresponding one there is y1. If that's x2, then that's y2. Now, there was no reason, you didn't have to pick that one if you didn't want. You would have called this x2 here, and the corresponding y2 would have been 13.17. So, example 3, we're kind of going up in complexity a wee bit. In this example, again, the gaps are not regular, so it's hard to spot the slope, but now we know how to do a slope formula. And this time, we're not quite sure what the initial height is. So there's an extra layer of complexity this time. But let's make a wee start. So first of all, we'll find the slope using our school formula. So we've got x1, y1. So take that first point there to be x1, y1. And we'll take the values at the end this time. We'll call that x2, y2. That one there could have been x2, y2. The important thing is once you pick a particular x value, use the corresponding y, or a particular time corresponding height. So calculating that then, y2 15.87 minus 7.81 gives us 8.06 over x2 minus y1 7.9, take away 1.7, and that gives us 6.2. So the slope is the vertical divided by the horizontal, or y2 minus y1 over x2 minus x1. So 8.06 divided by 6.2, m, the slope, is 1.3. Now, in the previous example, we knew what the initial height was because we were given the time 0, we had the height. But here we have to do something a wee bit different. Now, do you remember we're working towards this school formula here? Y equals mx plus c. Now, if we take mx away from both sides, we can say that y minus mx is equal to c. So suddenly we've got a formula that works for c. So just switching the sides around, c is equal to y1 minus m by x1. In actual fact, c is equal to y2 minus m by x2. You can fill any of those points in to work out what the c is. We know the slope, and then just pick any of these points you like. But just to keep it fairly consistent, we'll just use the x1 and the y1. So using that little formula then, what's the initial height? What's the c value? So c is equal to y1, 7.81, minus 1.3, which is the slope, times the x1, 1.7, and that gives us 7.81 minus 2.21. So c is equal to 5.6. So again, we had y equals mx plus c, or h equals mt plus c. So h equals 1.3, which is the slope, m value 1.3t plus c plus 5.6. So h equals 1.3t plus 5.6. And now you could check that. If you pick any of these points here, if you pick that second point there, or the third point, if t is 7.1, fill 7.1 in for that t there, multiply by 1.3, add on 5.6, and you end up with 14.83. And likewise, you pick any of the other times. Now, the good news is most of the time we're actually going to be told the relationship between the time and the height. So you don't have to go through what we did. But it's no harm to have that background that we're just after doing. So supposing for another javelin we had h equals 6t plus 5. T is the time in seconds. H is the height in meters. What's the initial height of the javelin? So if the time is 0, 6 times 0 is 0, plus 5, so h is equal to 5. But you knew from the y equals mx plus c, that's the initial height anyways. So that's just detailing that there. What is the slope, and explain what it means? Well, the slope is 6. And what does that mean? The slope is 6 meters every second. The javelin rises by 6 meters every second. So over the space of every second, it rises by 6. So for every 6 meters, so for every second in time, it rises by 6 meters. If t is equal to 3.8 seconds, calculate the height. So all we do is substitute 3.8 in for t. So h is equal to 6 times 3.8 plus 5, and that's equal to 27.8 meters. If the height is 53.6 meters, calculate the corresponding time. So again, use your formula. H is 6t plus 5. Substitute 53.6 in for h this time. 53.6 is equal to 6t plus 5. Take 5 away from both sides. 6t is equal to 48.6. And then divide both sides by 6. So t is equal to 8.1 seconds. So at the time of 8.1 seconds, the height of the javelin is 53.6 meters. Okay, so in this final example, we have an application where there are two different things happening. Initially, the javelin rises for a period of time, and then it falls off in value. So it follows two linear paths. So it follows that linear path there for a wee while. I equals 8t plus 3, that's the equation of a line. And then it follows the equation of this line here. I equals minus 4t plus 51. So we're going to ask a few questions here. What is the current when t is 3.6 seconds? So there's 3.6 on the time axis. And you might ask the question, which of these will we use? Well, obviously, between the time of 2 and 4, you can see we're using this line here. So we'll use the I equals 8t plus 3. What is the current when t is equal to 8.3 seconds? So 8.3, we'll use the second equation. When is the current equal to 24 amps? Well, 24 is about there. So the current is equal to 24 amps at about that time, 2 point something. And it's also equal to 24 at maybe 6 point something. The slope of the first line is 8. Explain what does this mean in terms of current and time. What is the average value of the current between 2 seconds and 12.75 seconds? So basically, the javelin has different heights all the way along, but what's the average height? So, first question. What's the current when t equals 3.6 seconds? So we already said we'll use the first equation. So we substitute in 3.6 in for t. So t is 3.6 seconds. I equals 8 times 3.6 plus 3, and that's equal to 31.8 amps. So 3.6 is about there, and you can see it looks to be about 31.8 amps. What is the current when t is 8.3 seconds? So 8.3 is the second equation. So I is equal to minus 4t plus 51. Substitute 8.3 in for t. Minus 4 by 8.3 plus 51 is equal to 17.8 amps. So 8.3 seconds, and it's about 17.8 amps. You can roughly see there. So, in the third part of this question, we ask, when is the current 24 amps? So 24 amps is about there on the vertical, and you come into the first linear line and drop it down to the time axis. It's about 2 point something. Come across the second line, drop it down 6 point something. So I equals 24 amps. So substitute 24 in for I in the first line there. So I equals 8t plus 3. 24 is equal to 8t plus 3. Take 3 away from both sides. 8t is 21. divide both sides by 8, t equals 2.625 seconds. So that's that first time there when the current is 24 amps. So 2.625. So the second time we substitute 24 in for I again in the second line. So 24 is equal to minus 4t plus 51. So algebraically we can think about this in several ways. But why don't we just add 4t to both sides? So 4t plus 24 equals 4t and minus 4t is 0. So simply on the right hand side we get 51 when we add 4t to the right hand side. So 4t plus 24 equals 51. 4t equals 51. Take away 24. Take 24 away from both sides. T equals 27. Divide by 4. Or alternatively in school, when you were solving that there, you might have said take the minus 4t over to this side and it becomes plus 4t, and that's fine as well. Now in the fourth part of the question, the slope of the first line is 8. Explain what this means in terms of the current and time. So there's the first line there, and the slope is 8. What does that mean? The current increases by 8 amps every second, or the current increases by 8 amps per second. And likewise, the slope on the second line is minus 4. The current decreases by 4 amps every second. Now, earlier on, we were talking about the slope, and we drew two graphs that had a positive slope. So that's a graph that's got a positive slope. This has got a negative slope. So if you notice, it goes the opposite direction. And the final part of the question, what is the average current, or what's the average value of the current between t equals 2 seconds and 12.75 seconds? So the current is 0 at 12.75, but we'll check that. So the current so those heights at different times represent the value of the current at different times. So what's the average current, or what's the average height? So really what we want to do is, we get the area under the graph, and imagine that we want to get that area and reassign it to be the area under the rectangle between the value of 2 and 12.75. So you can roughly see that area gets squeezed into there, and that bit maybe that bit tiny bit is there as well. So the idea is, if we can get the area under the graph and think about it then as a rectangle, and we know that length, and if we know the area, all we have to do to get the average value or the height is divide the area of the rectangle by the length. So we're interested in getting the area under the graph. So the average value is the area under the graph divided by the length along which we're considering it. So in this case, it's from 2 seconds up to 12.75 seconds. So just to clarify, I equals minus 4t plus 51. When is the current 0? So put 0 in for I there. 0 is equal to minus 4t plus 51. Add 4t to both sides. 4t equals 0 plus 51. Divide both sides by 4. T equals 12.75. So we know that value there is 12.75. So the length of the line is from 2 up to 12.75. So that means the length of the line is 10.75. 12.75 take away 2. So the length of that line there is 10.75. So obviously we start at 2. So if the time is 2, I equals 8 times 2, substitute 2 in for t. 8 2s are 16 plus 3 is 19 amps. So that first height there, that height is 19 amps. If t is equal to 4 seconds, substitute 4 in for t. 8 4s are 32 plus 3, so I equals 35 amps. So there's the 35 along there. Now, at t equals 4, the two lines meet. We didn't specify that in the question, but just to mention it here. If you fill 4 into the second equation, you get minus 4 times 4 is minus 16, and minus 16 and 51 is also 35. And at 12 equals 7.5 seconds, the height is 0. We already had that in the previous slide. So we divide the area. We mentioned we want to get the area under the graph. So we divide it up into 3 sections. So we've got what we call rectangle number 1, triangle number 2, and triangle number 3. So again, t equals 2 seconds, I is 19 amps. So rectangle 1 has got a height of 19 amps. We just go general, we call it 19. And the length of the rectangle is 2. So it's obvious now what that area is going to be. Triangle number 2 has got the same length. There's the length there of 2. But what's the height of the second triangle going to be? Well, the height is 35 take 19. So that height there is 35, but the height of the rectangle is 19. So 35 take 19 is equal to 14. So the height of triangle number 2 is 14. The length of it is also 2. Triangle number 3, the height is 35, and the length, do you remember we said the original length from 2 up to 12.75, that's 10.75, but the length of triangle number 3, we take away 2 from the 10.75, so that's going to be 8.75. So summarizing that information again, rectangle number 1, the height is 19, the length is 2, so the area is going to be 2 by 19, which is 38. Triangle number 2, the height is 14, which we said a minute ago, the length is 2, and the area of these triangles, they're right angled triangles, the area is half the base by the height, or half the length by the height. So triangle number 2 is half the length, half of 2 times 14, which is half of 2 times 14, half of 28, which is 14, or half of 2, which is 1 times 14. So the area of triangle number 2 is 14. Likewise for triangle number 3, height is 35, length 8.75, area is half of 8.75 times 35, and you can check that out. That area is 153.125. So again, summarizing the areas that we just found, rectangle number 1, area 38, triangle number 2, area is 14, triangle number 3, area is 153.125. Now, technically, I'm not mentioning units for the area. Technically, it's time multiplied by current. If you want to be technical about the units. And for the enthusiastic student, if you multiply current multiplied by time, you end up with charge. But that's another day's story. The total area is 205.125. So now we have the total area, and imagine that as the rectangle that we talked about earlier on. So effectively, we now have got a rectangle, and the area that is the same as the area under the graph, and that area is 205.125. The length of the rectangle is 10.75. What's the height? And the height of that rectangle corresponds to the average current between 2 and 12.75. So the average current is equal to the total area, 205.125, divided by the length, which is 10.75, and that gives us an answer of 19.08 amps. So we hope you've enjoyed this video, and we look forward to seeing you the next time. Thank you very much.